a little bit of an anomalous sensor reading. And that avoided a problem, and we didn't spend more energy going through that. So that technology is one that maybe isn't quite as dramatic as a late orbit software reboot, but nonetheless gave us confidence going through the mission.
Great. Thank you so much for your insight on that. Next up, we have Ken Chang with the New York Times. Ken?
Yes, hi, thank you. I was wondering, I guess for Tim and Steve, sort of a tick-tock of what happened after lunar insertion. It looked like the orbit was lower than what was in the press kit, and then you had another burn that evening, and then you avoided the DOI burn, and then you had it moved up the the landing time. So I was wondering what the various orbits were and how that affected the landing time. And also, when did you find out that you had a bum laser altimeter?
I missed the last part. I'll start with the first part. Kenneth, do you want to ask the last part again?
When did you find out that you had a bum laser altimeter?
Yeah,
Oh, okay, laser altimeter. Yeah. So the first part of the question was about the lunar orbit insertion and what happened after that, right? If I understand your question right. Well, we were having some difficulty with communications around the world, communicating from the different configurations and the different dishes that we had around the world up to our radios. And we have Quasonics radios and Thales Alenia radios. And some of those Thales Alenia radios have a range beacon, and we have a frequency that we know, a carrier frequency that we're operating on. And some of the dishes were smaller around the world. So in certain parts of the world, we had a weaker signal, and we would lose that carrier lock. And when that carrier lock goes down, you can't get a good orbit determination. And there was a shift in the ranging beacon, so that shift and that turnaround ratio in the ranging beacon is such that you had some inaccuracy. We had some inaccuracy. So we got the best data we could possibly get going into our lunar orbit insertion burn. But what we found was that was slightly elliptical. Actually, it was elliptical, not highly elliptical, but it was elliptical orbit. And so we were not comfortable necessarily with the proximity to the South Pole area. We were a little too close for our own comfort. So we decided to come in and do a raise of our paraloon position, and we did that very quickly, autonomously, and put us in a safer configuration for the mission and be prepared. And that burn we did in such a way that it eliminated the need for a deorbit insertion burn, a very small burn, before we did powered descent. When we were looking at our position around the moon, we decided to take a laser rangefinder, power it on, and ping the surface to see how close we were, because we were having trouble with this orbit determination and this Doppler measurement that we were trying to get. And we saw that that laser didn't fire. And what we found was that there's a safety enable switch, because it's not an eye-safe laser. That safety enable switch is in the box and was not disabled. So it's like having a safety on a firearm. It's for ground processing, and that was an oversight on our part. And so those laser range finders could not be turned on, and we couldn't manipulate that enable switch or disable switch with the software. And so those rangefinders had been tested and would have worked if we'd had caught that oversight and removed that enable before or disable before flight. So I think that got your question. Tim, anything to add on that?
No, that's right. I think the key thing was we have an incredible flight dynamics team who were able to determine that from the orbit we were in, we could raise paraloon with a lunar correction maneuver that they had built in with the foresight to trim the orbit if we had some unexpected conditions. And it basically put us into our descent orbit about 4 or 5 revs before we nominally would have done that. But the orbit still phased over the landing site in the right way and gave us a great opportunity to execute powered descent.
Thank you so much for that. Lauren Grush with Bloomberg.
Hi, thank you so much for taking my question. I think this might be for Steve or Tim. I'm curious if you've been able to determine if the tipping damaged the lander at all based on the rock that it's leaning on. Is there any concern of further degradation because of the position that it's in? Thanks.
Well, again, Lauren, we're hopeful to get pictures and really do an assessment of the structure and assessment of all the external equipment. We are hopeful that the top deck solar array is not damaged, and that as the sun comes around the lander, we'll be able to get some power generation from the top deck solar array, which is now vertical. And so we'll see what that means. But so far, we have quite a bit of operational capability, even though we're tipped over. And so that's really exciting for us, and we're continuing the surface operations mission as a result of it.
Thank you. Next up, we have Andrea Leinfelder with the Houston Chronicle. Andrea?
Hi. These questions are for Tim Crane. That final orbit you took, I just want to make sure that was specifically to implement the software patch to use NASA's LiDAR tech demo for landing. Also, Tim, on Twitter, or excuse me, X, you mentioned a big roll maneuver. Was this part of the plan? If not, what caused the roll maneuver, and did that create any complications? And finally, I was hoping you could walk us through some of the communication issues experienced right after landing. Was it difficult to get a signal because it was at an angle, or was it other challenges related to being on the South Pole? Thank you.
Thanks, Andrea. I did not catch the first part of your question. Could you repeat that?
Sorry, the first part was, that final orbit that you took that kind of pushed back the landing. Was that specifically to implement the software patch that helped you land with the NASA's LiDAR tech demo?
Yes. Okay. Thanks. It was. We were in good position to land at approximately 3:30, but the procedures that Steve was talking about. What order do we bring down the flight control, the guidance? Do we inhibit RCS? How do we do that in such a way that there's no unexpected consequence on the vehicle? For example, if we turned off guidance, navigation, and control, but didn't turn off the RCS control valves, they could listen to noise on the computer instead of controls to zero, and we could open up the valves and lose control. So we were very, very deliberate about working through in what we call a flat sat, which is basically the spacecraft equipment laid out in a lab driven by a simulation. We were very deliberate about working that procedure so that when we shut the software down, we could bring it back up safely and there was no harm to the vehicle. We had the patch ready in time for the first landing attempt, but we hadn't come to a satisfactory procedure yet, and we had to get it right. And so Steve and I conferred. It would be a little bit more fuel to catch the orbit once around. But again, our flight dynamics and automation team had written software that gave us a great amount of flexibility to control Odysseus. And we're really at a special time in our lunar program at Intuitive Machines, where most of our operators are also the subject matter experts who built these systems. So we had incredible insight what was going on. We had great confidence we could make this work, but we needed a little bit more time. And so we made the call to abort once around and implemented the patch at that time, so that when we had that final orbit, we were in high confidence of landing. The roll maneuver at the end, we had made some decisions. Every vehicle has a mass limit, and you're trying to optimize performance versus mass. We had flown a vehicle with fixed antenna, and in order to fly with fixed antenna, we had to look at what our landing orientation was. At the South Pole, we landed. In fact, you'll see in this model, there's white paint on some surfaces and black paint on others. That's because we were going to land on the south near the South Pole, and the sun was going to illuminate the solar arrays, as you can imagine, and then also these white surfaces to reject heat. But on the other side, we have the cold side, and it gets very, very cold if you're not in direct sunlight on the moon. So we painted that black to catch reflected light off the moon and warm them up. So as we were coming down, we wanted our navigation cameras pointed to the ground. Then we wanted our navigation cameras pointed to the ground after we pitched over. But in landing, we had a planned roll maneuver to bring our antennas to face the Earth. And so in order to accommodate that, we had a planned roll maneuver. It was not unexpected that the roll maneuver would occur. It was also expected that there would be a loss of communications as we switched from our 1-2 antenna pair to our 3-4 antenna pair.
Thank you so much for that. Next up, we have Chris Davenport from the Washington Post. Chris?
Hey, thanks, everyone. For Tim and Steve, just regarding that audible you had to make, and I want to see if I can hone down on some of the chronology to get a sense of how the day unfolded for you yesterday. About what time is it that you realized that laser rangefinder wasn't working? And then did you immediately know that you could go to the NDL system? Was this something you had planned on as a contingency, or did you kind of make this up on the fly and decide, work on it, in real time yesterday? Thanks.
I'll start, and Tim will add a lot of color to this because this one was, like Gina asked, was the Hail Mary issue. When we went around the night before and we made that laser rangefinder measurement, it looked like the laser fired. We got an enable in the data, but when we did a deeper analysis of it, it was not actually fired. It was an error in the telemetry. So when we dug into it, we that morning, this was the morning of landing, we called MDA and asked them what they thought about it and could we convert that physical enable switch to a software change to command that switch, and they indicated no, there's a physical cutout for this and not a software-driven cutout for this. So I get into the control room, I can laugh about it now, and Tim was on console as the mission director, and I said, Tim, we're going to have to land without laser rangefinders, and his face got absolutely white because it was like a punch in the stomach that we were going to lose the mission. And we went around and we said, what are we going to do? We started to hack into the OS, the operating system of the laser rangefinder, to see if there was a way we could trick it some way. We thought about running a simulated table of the powered descent phase and predict with some parameters how we might land, and there's just way too many variables in that running a simulation table against a real world situation, so that wasn't going to work. And so Tim and I were walking through the halls and trying to find the experts, and he came up with the idea that says, why don't we just plumb the high beam laser and the low beam laser from the NDL into the registers for the HRN laser rangefinder and the TRN laser rangefinder. He came up with that while we're walking down the hall in a hurried way, and it only would work if we ingested the range measurement in the nav application, and we had done that because we had worked with the team at Langley for so long with the NASA Doppler LiDAR that we were able to have that instrument in shadow mode to give them better quality data. And because it was in shadow mode, we had that measurement in the navigation application, and it was just a brilliant piece of insight by Dr. Crane to say, let's clear the register and put those two lasers in as the actual makeshift laser rangefinders. So that's kind of how it unfolded, and we needed more time, so we delayed and took the risk and said, let's delay an orbit and switch to a later landing time, because the landing time was originally around 3:23 or 3:24, and we delayed till 5:24, as you know, based on a 2-hour orbit around the moon. So Tim, anything else?
Yeah, it sounds easy in retrospect. We had the navigation Doppler LiDAR already plumbed in the navigation system and had the range rate data, so the 3 beams on the NDL produce a velocity measurement, as Prasoon had talked about. They also produce a range measurement. And we were not using the range measurement. We had just the range rate as a backup to our optical systems. But because it was already plumbed in there, we had to rewrite time tags into our measurement loader. But the challenge was the lasers. So we have these 2 navigation pods on the vehicle. If you can zoom in there, maybe not. Anyways, there are these 2 navigation pods that have the cameras. There you go. 2 navigation pods on either side of the vehicle that have cameras, and the laser rangefinders point in the same direction as the cameras. And those angles were optimized for our flight trajectory to give us the best measurements to land softly. The NDL was under one of these, And its angles were optimized to test the extent of its performance, not necessarily to feed our navigation system, but to test the sensor because it was a technology development. So after we figured out we could write the measurements into the laser rangefinder, we had to quickly tell the computer that the laser beams were pointed in different directions. And so there were a number of attitude transformations of it's not in the same location, it's not in the same orientation. And if you've ever seen engineers doing right-hand rule transformations, there were a lot of broken wrists, put it down here, as people were trying to figure out which way is it pointing. And I will tell you that in normal software development for a spacecraft, this is the kind of thing that would have taken a month of writing down the math, cross-checking it with your colleagues, doing some simple calculations to prove that you think you're right, putting it into a simulation, running that simulation 10,000 times, evaluating the performance. Usually you find an error because you did something in that rotation wrong, and you roll it back and you go again. Our team basically did that in an hour and a half. And it worked. So it was one of the finest pieces of engineering I've ever had a chance to be affiliated with.
I'd like to add to that the performance of the navigation Doppler leader technology and a payload that was developed by NASA's Langley Research Center was outstanding, and it was reliable. And that's what got Intuitive Machines some of the key data they needed in order to soft land.
Great, thank you so much for that. Eric Berger with Ars Technica. Eric?
Hi, thanks very much. Congratulations. Two questions for Tim or Steve. First of all, about propellant management. I'm curious how the cryogenic boil-off matched up with your expectations and kind of how much prop you had left at the end. And then what is the data transfer rate you're getting now versus what you expected? You know, trying to get some sense of how much data you're going to get back over the next week or so versus your original expectations. Thanks.
Propellant. So actually, the cryogens did very well. And just a correction, Eric, our system doesn't really have boil-off. Our tanks are rated to hold the pressure of the methane. It's very close to space storable. Really, what we're worried about isn't a propellant boil-off. It is temperature management. We want to keep that cryogenic fluid very cold because the density of that fluid in our engine is what gives us the power of that thrust system. So really what we were looking at throughout the flight was, did our insulation plan and our isolation of the cryogenic tanks from the hot material of the spacecraft, did that give us the right thermal protection so that we did not heat that cold system up? And that worked very well. We found ourselves in a very good situation with propellant all the way through the mission. We used a little bit more helium than we thought through the mission, and had to adjust our control approach for that. And that was probably the area of concern. We were running a little bit low on helium. So a lot of lessons learned there on how we'll manage that going forward that will play out very well. And in terms of the bandwidth, that's difficult to answer. One of the things that's happening right now, we built fault detection technology into our comm system that if we're not getting a command heartbeat up on 2 of the antenna pair, it will go through a sequence of powering the radios off, restarting them, and then if they still don't get the heartbeat command signal from the Earth, then it switches to the other antenna pair. And so one of the first things we're trying to do is get out of that flight configuration and stay locked in on 2 antennas. But with that flip-flopping back and forth, right now we're trying to get the command up to move out of that flight mode, but there's a beat frequency of we go from a good configuration to one that's down, and then we're about to come up to the new one, and we move to a new antenna. And so we're working through that. When we left to come over for the briefing, I think they just about had that solved, but I can't give you a strong number because there's a variability there as we go from different antennas to different dishes around the world.
Great, thanks again. Jeff Faust with Space News. Jeff?
Good afternoon. Maybe just to quickly follow up on Eric's question for Tim, what is your best guess at how good the data rate you can eventually get once you optimize the system for the lander and its configuration? And then also, I think this question was asked earlier, I may have missed the answer. What's your best guess in terms of margin of error of how close you are to the predicted landing site? How many kilometers away do you think you touch down? Thanks.
Yeah, great questions. Thanks, Jeff. Best guess, in terms of bit rate, that's hard to say because that does vary with the antenna size and the sensitivity of each antenna, but we expect to get most of the mission data down once we stabilize our configuration. In terms of landing accuracy, you know, without precision navigation sensors on board, the best you can expect to land on an IMU-only landing system would probably be in the 4 to 5 kilometer range. However, our optical navigation sensors perform flawlessly. In fact, our optical measurements looked better on the scopes than they had in simulations. So I'm confident that we're well within probably a 2 to 3 kilometer accuracy of the landing site for this mission. Would have been better if we'd have had our full complement of sensors as expected.
And just as a closing point, Jeff, on this question is that we're planning, working with the Lunar Reconnaissance Orbiter and the Arizona State University faculty to do a pass to see if LRO can locate our position precisely and give us a latitude and longitude. And we expect that measurement, that pass to occur this weekend.
Thank you so much for that. Joey Roulette with Reuters. Joey?
Hey, thanks for doing this. Question for Tim or Steve. Since the lander is on its side, I was wondering if you could go into how that will limit what the lander can do, which operational capabilities are impacted by that, and which science objectives, if any, won't be able to be conducted because it's on its side. Thanks.
Well, I'll comment initially. Like I mentioned, we don't have active payloads on the panel E, I believe, is what's facing the surface of the moon. And so therefore, the active payloads that need communications and we need to command and we get the telemetry out are all exposed to the outside, which is very fortunate for us. We do have antenna, however, that are pointed at the surface, and those antennas are unusable for transmission to Earth, back to Earth. And so that really is a limiter. Our ability to communicate and get the right data down so that we get everything we need for the mission, I think is the most compromised from being on our side. Anything I missed, Tim?
No, that was it.
Well, maybe one I just thought of is I was telling you before about the solar panel on the top deck. We had to angle that at about 30 degrees tilt up for landing on the South Pole. That was one of the engineering changes we made when NASA asked us to move towards the South Pole region. Now we've tipped over and we don't know the health of that solar panel. It would be great to get a picture and or wait until the sun comes around and see if we get any battery charging off of that solar panel. So we'll see. We're in a great state of charge with the batteries. We're getting plenty of sun on the horizontal, the now horizontal solar panel, and we'll just have to wait and see with that other panel.
Thank you so much. Jonathan Siri, Fox News.
Thank you for taking my question, and congratulations, everyone. My question is also for Tim or Steve. Your team had to essentially rewrite the instruction manual several times while in flight, not just for troubleshooting, but also adapting to first in space performance of that new engine. Could you give us an idea of how many people were involved with the process, and did the discussions take place in a single war room, or were you conferencing in experts from multiple locations? Just give us an idea of the human logistics involved.
So I'll give you a rough overview, and then Tim can comment kind of how it went over the 7-day period. The operations team was structured into 3 shifts, red, white, and blue shift. Those shifts were supposed to work 8-hour shifts and then do a handover between shifts, but between those teams. Those teams are about 10 individuals.
Yep, 10.
And the other team that we activated was called Team 4. And the Team 4 was a handful of us senior leaders and engineers that could analyze and take the workload off of the operations teams. So if the operations teams are wrestling with a particularly thorny problem, they would call Team 4 and say, get in here and let's work on this for us and give us a solution. So we would pull in the subject matter experts for any of the disciplines that we would need to solve any particular problem, and we would work in a war room sense outside the control room to tackle that problem. We would have, for example, to activate and bring up the simulation or activate and bring up the flat set. We would run analysis cases. We would call the vendors, like we called MDA about the laser rangefinders. We called NASA and talked about the Deep Space Network with that orbit determination need. So all of that chatter in the back, that was handled by, I would say, about 30 people that would work a given problem on and off based on the discipline. But what had happened during the mission was that red, white, and blue team and teams and Team 4 ended up working nearly around the clock. We really could have staffed more, but it takes a lot of expertise to staff those teams, and we ended up kind of melding into, we're all working on this last problem through powered descent, and we collapsed into a single red, white, and blue team, all of it, to get that solved, which we're going to go back and look at and see. You know, we really, really worked the team hard. They put a lot of hours in. I think one of the longest days was 48 hours long, and another day was 40 hours long for some of the folks, and that's, you know, just working too hard, and we need to give them rest so they can be bright and make the right engineering decisions. So we got some lessons learned in that area, but we did it, and it was worth it, and it was a whole idea of persevering through the challenges and never giving up. Never, ever give up until the last-ditch solution you could find, and then keep thinking about it if it didn't work. So just a testament to a great operations team.
Yeah, I'll add to that. You know, our operations concept was a blend of human spaceflight for space station and space shuttle. We have, you know, that's in our culture here in the Houston area. Some of us had worked on the All-Hat Morpheus project at NASA, which was in some way has the DNA that led into Nova C. We had people with a military operations background, and then we had people from commercial networked operations. And so we put all of that together, and we came up with our own unique blend of how we were going to do spacecraft operations. And a big focus of that was the people inside the room on the red, white, and blue teams, keep the vehicle alive. Keep the vehicle alive and doing what it's supposed to do. And then all the mission directors, myself, Jack Two-Fish Fisher, and Trent Martin, we had the responsibility to interface with Team 4. And we would be able to say, I have this problem, I can't solve it with the resources I have in the room, and do what we're supposed to do. And so we would shed those out to Team 4, and they did an amazing job, whether it was talking to the vendors or developing a procedure. They took that off the plate, and that load balance, even though Steve's right, you know, I joked this morning that, you know, how was your day? I said, well, this mission was the longest 7-day day of my life. But it really allowed us to focus on keeping the vehicle alive and keeping it moving on its way to the moon and doing the things we needed to do while problems and anomalies could be solved in the back room. And, you know, this is a story that everybody on that team is going to be able to tell for generations about how we landed.
Irene Klotz, Aviation Week. Your line is open.
Thanks. If I understand that incredible sequence of events correctly, was it just serendipity that a situation developed with that elliptical orbit that caused you to try and get the laser rangefinder data where you realized it wasn't working before it would have actually been needed? And when during the touchdown would that laser rangefinder nominally have been activated?
I think I understood, Irene, the question. It was actually fortuitous that we had an elliptical orbit after lunar orbit insertion, because we would not have arbitrarily activated the laser rangefinders prior to powered descent. We tested them on the ground. We flew them on aircraft. We flew them on helicopters. We assumed after all that testing they worked. So the first usage of those laser rangefinders was supposed to be during the powered descent. But because we had such a low paraloon, we activated a laser and found the problem. So that was fortunate, and that was a bit of luck for us that then we identified that they weren't firing. So at that point, then that was recovered. Like I said, at the next morning we uncovered that, and then we had to work feverishly to figure out an alternative solution. Anything there, Tim?
Yeah, just the second part, Irene, of your question of when would they normally have come on? Normally, we would have turned them on after deorbit insertion about an hour before landing, and we expected what we call the terrain relative navigation LiDAR, the laser rangefinder, that would have operated really from about 50 kilometers altitude all the way down to landing, and then after pitch over, we had a laser on the other side that would take us from a kilometer down. So we would have probably been 5 minutes to landing before we would have realized that those lasers weren't working if we had not had that fortuitous event. So serendipity is absolutely the right word.
Jackie Waddles, CNN.
Hi, everyone. Thanks so much for doing this. I had a quick question for Steve or Tim. I know everyone's really curious about the photos here, so do you guys have any indication if EagleCam is in a position to pop off the lander and take some pictures? And to that end, if you could just clarify for all of us, are there any specific payloads, whether commercial or NASA, and I know some of them are passive, and you're still working on figuring out these data downlinks and stuff, but are there any that you know for sure or just haven't gotten any data yet and don't know if you will get data from? Thanks so much.
Well, fortunately, again, EagleCam sits on a panel. Let me show Tim. If panel E, I believe, is towards the surface of the moon, EagleCam sits over here on this panel, and we plan to eject that camera off the side, so it will fall about 30 meters or so, maybe not that far, away from the lander and get a good shot of the lander position this way. So we're looking to power up that EagleCam. We were waiting on getting commanding ability, power that up, clear that SD card, and fire the camera, and so we can get a view back to our lander. So that's a very exciting image for us. The reason it wasn't fired as we were landing was because of this nav system initialization that we had to do, which put a flag up to flag the EagleCam not to fire. So that was part of the troubleshooting we had to do to get the Doppler LiDAR into the nav system. We had to do these navigation initializations, and that shut off the EagleCam. And we knew that was in the software, but we just did not have time to go fix that. And so now we'll get it and get the image in the orientation that we need. The other question you had about commercial payloads, we think we can meet all of the needs and from the commercial payloads that we have in the orientation we have. The one on panel E that's covered right now or shaded by the lander and the surface is the ArcCube project, and we believe we've got an image of that already that we can download and share with our customer.
I'll add that for the NASA science payloads, as we said earlier, that many of them have already taken a lot of data, a lot of measurements in transit and also on descent. We're still checking to see if in the current suspected orientation of the vehicle, whether there will be any particular measurements that can't be made in some of the payloads. So for example, we want to make sure that the laser retroreflectors, which are normally pointed up, so that when the Lunar Reconnaissance Orbiter flies over, it can pulse them with a laser beam and find their position. We'll have to check to make sure that they can still be illuminated. They probably can be when the orbiter is flying at a further angle away on the trajectory. Very similar to what we found with the recent SLIM landing from the Japanese Space Exploration Agency. But we are doing an assessment to see are there any measurements still to come that from any of the NASA-supplied payloads that most likely can't take place, particularly because of this new orientation.
Great, thank you so much for that. Will Robinson Smith for Spaceflight Now. Will?
Yes, hi. Thanks for taking the time to answer our questions here. One for Joel and for Sun, if I could. Given the success and now the operability of the NDL, will that become a, I guess, highly recommended or required payload on future CLIPS missions? And what are the potential implications or knock-on effects for the human landing system landers? Will NASA recommend that Blue Origin and SpaceX implement that into their landing systems? Thanks.
I'll take a shot for Sun, but please add. So for a commercial lunar payload services initiative, we don't prescribe to the company partners that are doing this as a service, what techniques or technologies they use. But as you can imagine, all these different companies are always looking for low risk, good performance ways to gather the data or conduct the operations that they are going to conduct for NASA. So I'm sure that this story, as you can tell now, is very public about things like the performance of the NDL, and we would think that people that are looking at lunar landers would be checking into that technology now that it's actually been flight proven operationally on probably an unanticipated flight test mission, right? I actually use it operationally. I would say the same thing, the human lander system partners have their own techniques and their own approaches that they're taking, but again, now that this has been actually shown to operationally work, I would think it's going to be of great interest to folks that want to travel to the moon. Prasad?
Yeah, I will add, we've actually, NASA has already licensed this technology to a small company to commercially provide this to whoever wants to buy it, right? And so this only adds more validation of the system. There's just a technical reason to add it, right, beyond the aspects that Joel talked about, because it is an order of magnitude more accurate in precision and measurement of range and velocity components. It's half the power, half the mass of the traditional approaches that we've used in the past. And the volume in terms of size is about a third of it. So if you just look at it from a technical perspective, it just provides all these benefits. And so I'm sure future vendors will look at this type of capability anew and try to incorporate these types of technologies. And that's why we're doing these missions, right? Is to develop better and better capable systems that allow us to do this more reliably, more capably, and hopefully more sustainably and more cost-efficient wise. So in fact, after the landing, I did joke with Steve there. It's like, hey, now are you ready for IM2? Because we have 3 payloads already ready to go on IM2, right? And so we're ready to demonstrate even more stuff that will help the greater space economy that burgeoning in here in the U.S. And we just want to augment that as much as possible we can with what we're doing.
Yeah, I'll chime in as well. As you look forward to future missions, and as we begin delivering cargo missions with a metric ton and more, those payloads get more and more valuable. And as those payloads get more and more valuable, we're going to have to prove to our customers that we have robustness in our landing systems. One of the ways you achieve robustness is with redundancy or with dissimilar redundancy. So having 2 ways of measuring that landing. We had a camera system on board, but if you have a camera system and a laser system, one might fail in a way that the other one might not. And so I can see that as the lunar economy opens up, as NASA begins to send cargo and larger, more expensive payloads with companies like ours and others, that you're going to see demand for these kind of sensors complementing a suite of sensors that you use to guarantee safe landing is going to be something that will be an industry standard.
Thank you for that. We are going to try and take 2 more questions, so I'm going to ask you guys to be brief in your remarks so we can get through these questions. First up, we have Marcia Smith with spacepolicyonline.com. Marcia?
Thanks so much. Getting back to the communications question, I gather that part of the challenge is that you have so many different sites around the world with different capabilities. But I know that you had talked before you launched about the challenges of communicating at the South Pole. So how much of the comm problems are related to the ground stations and how much to the place where you are on the moon? And what lessons are you going to learn from all of this for the Artemis missions?
Well, yeah, I'll answer some of that question. what you get is a phenomenon at the South Pole that NASA's interested in understanding, since that's where our future Artemis missions are targeted, or NASA's future Artemis missions are targeted, is a frequency multipath condition. And so are you going to get multipath interference on your communication frequencies? Fortunately, we think the antennas that are pointed towards the moon will give us a really good understanding of that phenomenon at the South Pole. Another serendipitous moment, right? But I would say that we thought about this landing on the South Pole quite a bit, and if you look at the mock-up, all the antennas are up high and pointed like towards Earth when you're sitting on the surface of the moon. In transit, it's very difficult. You have to constantly change your attitude to point the antennas back to Earth when you're headed toward the moon. So we're going to figure out an antenna location map for subsequent missions, and even mission 2, that gives us an antenna pointed back at the Earth when we're flying out towards the moon, for sure. Also, in this first ever use of our lunar data network, this commercially now available data network made up of these large radio astronomy dishes that we've stitched together in a network, some of those dishes have had configuration issues. Some of those dishes have had a weaker power band. So we can all operate on this frequency, S-band set of frequencies. However, the power to reach the moon is what came into account as we went around and out towards the moon. The further we got, sometimes those power transmission levels were too low to have us keep the carrier locked up on the radios. So that was some of the challenges, and that's what we're looking for going forward, is to really regularize that lunar data network so that operationally we know the configuration. We can go upgrade to put additional orbit determination capabilities within our baseband units at each antenna site. And the best thing will be when we get our data relay satellites in orbit, we'll have that problem licked, and we can communicate short distance from the surface up to a satellite and relay that back to Earth in a more traditional way. So looking forward to those advances in the communication system.
Thank you. And we have one last question we can take this afternoon with Adam Mann from Science. Adam?
Hi there. I'm with Science News, actually, and I guess this is for the Intuitive Machines folks. I'm wondering, maybe you've answered this already, but I'm just wondering if you have any idea how long ODI might be able to stay operational on lunar surface.
Well, it's a great question, and you're going to bring a tear to my eye. We know at this landing site the sun will move beyond our solar arrays in any configuration in approximately 9 days. And so the early missions are all solar powered and require that. And then once the sun sets on ODI, the batteries will attempt to keep the vehicle warm and alive, but eventually it'll fall into a deep cold. And then the electronics that we produce just won't survive the deep cold of lunar night. And so best case scenario, we're looking at another 9 to 10 days. And then we will, of course, the next time the sun illuminates the solar arrays, we'll turn our dishes to the moon just to see if the radios and the batteries and the flight computer survive that deep cold. The solar array should survive the deep cold and provide power, but we'll just see if our electronics made it through. We'll take a look, we'll take a listen. By that time, we'll have gotten very, very good at listening to that signal, but we do expect probably a maximum of another 9 to 10 days.
Thank you so much, Tim. And thank you to everyone who submitted questions this afternoon. And thank you to our briefers for taking the time to discuss this historic mission enabled by the agency's Commercial Lunar Payload Services, or CLPS initiative. We hope you'll continue to follow along on this mission by keeping track on Intuitive Machines' website and on nasa.gov/CLPS. That will wrap today's briefing. Thank you so much.